Orbital period of a satellite. What we're looking at here is we've got our planet and we put a satellite up there and we want to know what its orbital period will be. Now if you just put a satellite up there, gravity is going to pull it straight back down. The only way we can keep a satellite up there is if all the gravitational force, weight force if you like, is being used to provide the centripetal force. So what's the force acting on a satellite? That's just our normal equation for gravitational force. Now the big M is the mass of the Earth and the little m there is the mass of the satellite. But if we make that equal to the centripetal force, which is v squared over r times little m, because it's a satellite that's got the centripetal force acting on it, then we can cancel out those m's, we can cancel out that r with that one, and we're left with g, big M, over r equals v squared. Now we want the period of the satellite, and the period of the satellite is going to be equal to the velocity, the period is going to be equal to the distance divided by the velocity, right? So the distance is going to be 2 pi r, that's the circumference, divided by the velocity. Alright, so if we go back to that, we can say v is equal to 2 pi r over t. If we square the whole thing, v squared is equal to this whole thing squared, which is equal to 4 pi squared r squared over t squared. So we can now make that equal to g m over r. Hopefully you did all this, and if we put the t squared up in that area there, we get rid of that gm, we put the t squared there, we put the big G, the big M here, and we put the r up here times r. Then we have 4 pi squared r cubed all over big G, big M equals t squared. So if we want that to be equal to t, we just put it all under the square root sign. Then we are done.